Hi everyone, I'm Omsing Pawar with my partner Manas Pandya, and today we'll be talking about Nomad, which stands for Non-Exclusive Memory Tiering via Transactional Page Migration. This paper came out of OSDI 2024, authored by researchers at UT Arlington and Intel Labs. At its core, Nomad is a rethink of how operating systems should manage memory in the age of CXL and persistent memory. And I think by the end of this presentation, you'll see why that rethink was long overdue. So let's start with the hardware context. For decades, the memory hierarchy looked like this: DRAM on one end, disk on the other, with a gap of 2 to 3 orders of magnitude between them. That gap was so large that any work you did to keep hot data in DRAM was absolutely worth it. But that world no longer exists. New memory technologies, CXL memory, persistent memory, attach directly to the CPU via memory buses, and they perform within just 2 to 3 times of DRAM. The hierarchy is now nearly flat, and that changes everything about how we should think about paging management. Which brings us to the core problem. Decades of OS design were built on one assumption: migrating a hot page to fast memory is always worth it because the performance gap is so massive. But with that gap collapsed, that assumption breaks down completely. Think of it like a seesaw. On one side, you have the access benefit of moving a page to faster memory. On the other side, the cost of actually doing that migration. When the hardware gap was huge, the benefit always won. Now, the cost can easily outweigh the benefit, and when that happens, your application usually slows down because of the migration, not in spite of it, and it gets worse under memory pressure. The existing approach is what's called exclusive tiering. A page lives in exactly one tier at a time. If a page is hot, it goes to fast memory. If it cools off, it gets demoted to slow memory. The problem is, in real workloads, the working set size frequently exceeds the capacity of fast memory. When that happens, the OS ends up in this continuous loop, promoting hot pages up, demoting cold pages down, promoting again over and over. This is memory thrashing, and the paper quantifies just how bad it gets. User perceived bandwidth can collapse by 95%, and not a small degradation, nearly a total collapse. The system spends all its time moving data and almost no time actually computing anything. So what do these existing systems do? The main comparison points here are TPP, which is transparent page replacement, which is Linux default approach, and MEMTIS, a more recent research system. TPP uses page fault based tracking, which is highly accurate, but its migration is synchronous, meaning the application CPU is blocked during migration. Every time a hot page needs to move, the application just waits. MEMTIS goes asynchronous using hardware performance counter, PEBs on Intel, which is off its critical path, but its sampling based tracking is coarse grained and misses a lot of pages, especially those that always hit the CPU cache and never generate a cache miss to sample. Critically, both systems use exclusive tiering. That's the fundamental limitation Nomad is designed to fix. Nomad is built on two pillars working together. Pillar one is transactional page migration or TPM. The key idea here is that migration should never block the application. It happens in the background like a transaction. Pillar 2 is page shadowing. Instead of deleting the original copy of a page after promotion, Nomad keeps it as a shadow in slow memory. This makes future demotions essentially free. No data needs to move. Together, these two mechanisms give you what the paper calls fluid non blocking memory. Pages can move between tiers without disrupting the application. Let me walk through how TPM actually works because the contrast with legacy migration is really stark. In the legacy approach, top path here, the migration starts, the page is unmapped. The application can't access it. The OS copies the data, then remaps. The user is logged out the entire time. TPM flips this. The page stays mapped and accessible throughout the copy phase. The application keeps running, accessing the page from slow memory if needed. Only at the very end, after the copy is done, is there a quick atomic remap to the point to a new fast tier location. So instead of hard block, you get a brief atomic swap at the end. The migration is decoupled from the application's critical path entirely. The transaction itself has three phases. In phase 1, Nomad clearly clears the page dirty bit and issues a TLB showdown. This establishes a clean baseline so we can detect any subsequent rewrites. In phase 2, the data is copied asynchronously while the user continues to read and write through the slow tier. In phase 3, Nomad checks the dirty bit using an atomic instruction. If the page stayed clean during the copy, transaction commits, the PT is remapped to fast tier. If the page was returned to during the copy, transaction aborts cleanly, the original mapping is restored, and it retires later. This is essentially optimistic concurrency control applied to page migration, and it means the window during which the page is truly inaccessible is reduced to just that final atomic remap, not the entire migration duration like in TPP. Now I'll hand over to Manas.
Now let's talk about the asynchronous integration and queuing. The integration into Linux works through a two-stage queue. Page faults in queue candidates into a promotion candidate queue. And once a page accumulates a sufficient fault signal to be classified as hot, it advances to a migration pending queue with a dedicated kpromote kernel thread picks it up and executes the transaction copy. The reason this two-stage design matters is that standard Linux LRU list management imposes up to 15 minor faults per migration just from bookkeeping overhead. By decoupling tracking from migration entirely and by passing the LRU path, Nomad eliminates that overhead at the source. The second pillar is the more architecturally novel contribution. In conventional exclusive tiering, promotion moves a page to the fast tier and the slow tier is released. Nomad deliberately retains that copy as a shadow page, maintaining an X-ray index that maps fast physical address back to the slow tier counterparts. The memory cost is intentional, and the justification becomes clear when you look at what it enables under pressure. When fast memory is exhausted and demotion is required, rather than copying data back to the slow tier, which is exactly the expensive operation you're trying to avoid when you're already trashing Nomad, simply remaps the PTE to the pre-existing shadow copy. No data movement whatsoever. The shadow eliminates the demotion right entirely, which turns out to account for roughly half the migration overhead in trashing scenarios. This is the mechanism that allows Nomad to degrade gracefully, where exclusive tiering systems like TPP effectively deadlock and IO. Now, talking about the performance. In stable phase, where the working set fits within fast memory capacity, Nomad catches TPP's bandwidth and outperforms Memtis by up to 130%. The Memtis gap is attributable to its hardware sampling approach. Pages that are hot but consistently cache resident never generate LLC misses. So they are invisible to the sampler and never get promoted. Nomad's page fault based tracking has no such blind spot. Now, performance of the trashing phase. This is where the paper's contribution is most clearly demonstrated. Once the working set exceeds fast memory capacity, TPP's bandwidth collapses to near zero. The CPU is saturated, servicing synchronous page faults, and cannot make forward progress. Nomad degrades gracefully and achieves up to 6 times improvement over TPP under peak trashing. Transactional migration keeps promotion off the critical path, and zero copy demotion via shadow pages means the system is never bottlenecked on data movement in either direction simultaneously. Now, talking about the real world application, the results hold on production workloads. On Redis, Nomad delivers dominant throughput improvement over TPP under memory pressure. On liblinear, execution speed improves by 150%. Importantly, the evaluation covers both persistent memory and multi-vendor CXL hardware. So these aren't artifacts of a specific platform. The gains are consistent across the hardware landscape that are tiered memory systems are actually being deployed on. Now, the synthesis. To synthesize, Nomad's argument is that exclusive tiering is a fundamentally broken abstraction for byte addressable memory. The performance gap that justified always migrate hot pages no longer exists. So the overhead of doing so now dominates. TPPM addresses promotion by removing migration from the critical path through optimistic transaction execution. Page shadowing addresses demotion by making it a zero copy PTE remap. The two mechanisms are complementary and together produce a system that remains stable under the memory pressure conditions where prior systems fail. The authors note that emerging lightweight TLB shootdown mechanisms in newer IS extensions will reduce the initiation cost of TPM further, strengthening the case going forward. Thank you.